Good afternoon and welcome to the second of our webinars in our series of 3. Yesterday we heard from Professor Simon Hands on the twin paradox, which covers special relativity. Today we're going to hear from Professor Prem Kumar on black holes and holography, which is general relativity, and by the name holography, I'm guessing touching on quantum gravity, but we'll hear from Prem on this. Tomorrow, we have the final in our short series by Professor Niels Madsen, who will tell you about our work, the work of Swansea University at CERN on antimatter, and then do a virtual tour of CERN. But for today, I think the number of people is roughly stable. So I think we're good to start. Prem, shall I say about the question and answer thing?
Oh yes, certainly. Yeah.
Okay, so if you're used to Zoom meetings, you will find that the chat feature is disabled. Instead of that, we have a question and answer. So near to the bottom, there should be something that says Q&A. You can use that to ask questions during Prem's talk. This is a live talk, so if there are pertinent questions that need to be answered immediately, Professor Kumar will answer those then. But I think the majority of questions we will leave until the end. My name is James Bateman. Sorry, I should have said. I'm the admissions tutor. I may have sent you an email to let you know about this talk. If you have questions about studying at Swansea or other aspects of the admissions process, then feel free to ask those. They will, of course, be left until the end of the talk. Okay, thank you. Prem, over to you.
Great. Thanks very much, James. And welcome to everyone who's here today. I take it some of you have already been to Simon's talk yesterday on the twin paradox, which was about time dilation and special relativity. Today, I'm going to talk about something a bit different. I'm going to talk about general relativity. And I'm going to talk about black holes. And some of this material might be stuff that you've read about in popular science books or articles, newspaper articles or magazine articles on science and advanced physics. But what my aim will be to somehow get across to you some of the exciting ideas that are going around at the frontiers of research today in the area of black hole physics and quantum mechanics. Okay. So that's more or less my aim, is to get across to you a glimpse of the kind of research that goes on in theoretical physics, which is essentially this, the study of the mathematical structure of the laws of nature. And this topic that I'm going to touch upon is one of the most exciting and active areas of research in theoretical physics. It has been for several decades now. So let me begin by sharing screen here. Okay, so I take it everyone can see the screen, and I encourage all of you to ask questions. This is a live talk, as James has already emphasized, and if you have any questions while the talk is going on, I would encourage you to ask these questions using the Q&A box. And if the questions are questions that I can answer immediately, I will do so. But you're, of course, welcome to ask tons of questions at the end. Keep the questions coming so that there is a flow in the talk. And if there are things that I've missed out, I can always look at the questions and try to fill in the gaps. All right, so this talk is about black holes and holography. So there are two main themes here. One is is black holes in the title, and the other is holography. And we'll take each of these in turns as we go along. So the talk, of course, is the subject of gravity. And I take it everyone has seen at some point of time, we have heard and we've learned that gravity is a force, and our understanding of gravity was first made very precise by the great Isaac Newton. And what Newton observed and was in fact he made very precise was one of the very first universal laws of nature. And he understood and deduced that the force of gravity, the force of attraction between two heavy objects or any two objects carrying mass is proportional to the product of their masses and inversely proportional to the square of the distance between them. So this is the famous inverse square law of Newton's, obtained by him around 1687. This is something that we've all seen I imagine all of you have seen in your A-levels. And it's a great law because it's one of those laws. It's often called the universal law of gravitation. And it applies to all massive objects in nature. Any kind of particle, doesn't matter how small, how big, they all obey the inverse square law. Or at least we thought that they obeyed the inverse square law for the force. Main things to note about Newton's law is that there is this constant of proportionality G, which is the famous Newton's constant. It's in the standard units, SI units. This is an incredibly small number. It's 6.67 times 10 to the minus 11. So basically says that if you take two objects, each of mass 1 kilogram, and place them a distance 1 meter apart, then the force between the two objects is 6.67 times 10 to the power minus 11 newtons. That's an incredibly tiny force. It's something that we wouldn't be able to detect in our everyday lives had it not been for the fact that the Earth is incredibly massive, and therefore, even though capital G is incredibly small, the force of gravity on us is amplified by the mass of the Earth, which is really heavy. So gravity is in general a weak force, but it becomes extremely important when we are talking about massive objects, astrophysical objects, planets, stars, solar system, galaxies, and so on and so forth. And it's the force that shapes the universe. So it's very important to understand that gravity is a weak force at short distances, but at long distances, this is the one force that really shapes the universe. So it's incredibly important for us to understand gravity in every possible way. So this was, of course, the situation for a couple of 100 years. People thought this is what gravity is all about, until another famous gentleman came along, Albert Einstein, and he formulated what we now call the general theory of relativity. And all of you have heard a little bit about the special theory of relativity, those of you who were in yesterday's lecture at Simon's lecture. Special relativity tells you a couple of things. One of the important things that special relativity teaches us is that the velocity of light, or the speed of light, is a limiting speed in nature. Nothing can travel faster than light. And the speed of light is independent of the reference frame. So no matter what observers you pick, the speed of light is always the same. It's given by c, which is 3 times 10 to the 8 meters per second. So I'm not going to talk about special relativity, but I'm just going to kind of sketching this as a background, a bit of a historical background, because it's special relativity which actually led Einstein to think very hard about gravity. Because after his great success in 1905, when he understood the special theory of relativity, which he understood because he was trying to understand the properties of electricity and magnetism. In particular, he was trying to understand the properties of electromagnetic waves as predicted by Maxwell's equations. And electromagnetic waves, of course, just another name for light. So what Einstein was thinking about was he'd got this special relativity. One of the most important things that special relativity tells us is that the speed of light is a limiting speed. Nothing can travel faster than light, which means that you can't transmit signals between 2 points at a speed which is faster than the speed of light. So Einstein was thinking about this question in the context of gravity, because Newtonian gravity tells us that the force between two objects, say the Earth and the Moon, is dictated by the inverse square law. What if we take the Earth and jiggle it slightly? Okay, jiggle it very quickly. What happens to the force of the Earth felt at the location of the Moon if the Earth is jiggled around a little bit? Does that force change instantaneously? And if not, exactly how do you repair or fix Newton's laws so that you can understand this effect? Now, obviously, the force cannot change instantaneously if Einstein's special theory of relativity works, because signals cannot travel faster than the speed of light, and they certainly cannot travel instantaneously. So Einstein was one of the very few people thinking very hard about this question of how to reconcile gravity with special relativity. And through a very complicated and beautiful chain of reasoning, actually, historically, this is one of the most wonderful examples of how science, and particularly physics, is done. Einstein understood special relativity in 1905, very soon after he started thinking about gravity. And he had these beautiful thought experiments in his mind that he was putting together. And with his immense intuition, he was arriving at a very general set of ideas. And at some point, he realized that his ideas needed very sophisticated mathematics, which he didn't know. And he had to learn that sophisticated mathematics from one of his colleagues, Marcel Grossman, a mathematician, who taught him the tool of differential geometry, which is an arcane branch of geometry invented by the mathematician Riemann in the 19th century. And it turned out that Riemann's invention of this differential geometry was actually the language that Einstein needed in order to formulate his theory of gravity, which we now call the general theory of relativity. The whole process took him close to 9 to 10 years, actually. So it was never a flash of brilliance. It was real hard work, making tons of mistakes, one step forward, 2 steps back, very often. And so, you know, it's a very beautiful illustration of how science actually takes place. It's lots of hard work, not just moments of amazing brilliance. So, what did Einstein find? Einstein found this beautiful equation that I've written down here at the bottom. It's not important to understand what the equation really means and what all the symbols in it means. I'm just flashing it here in order to illustrate to you that this is a very powerful equation. It's an equation that occupies, you know, a couple of inches on paper, but it describes almost everything that we know in the universe and that can interact by means of gravity. These equations, when you solve them, they tell us that the universe, they give us solutions which describe the expanding universe, which today we call the Big Bang. It contains solutions in it that we are going to talk about, which are black holes. It contains within it the physics that describes how planets go around the sun. So this equation is really amazing, and its basic content is that on the left-hand side, you have something that I would just call geometry for now. On the right-hand side, we have something that I would call physics for now. And so what this equation basically says is that on the right-hand side, when you have matter or energy, which is present, any distribution of mass or energy which is present in space-time, it actually curves the geometry of space-time in exactly the same way as is illustrated in this figure at the bottom right. This is kind of is an illustration that if you think of space-time as this bendy kind of sheet, whenever you place heavy objects in space-time, these heavy objects or any energy density will bend or curve space-time. And that curvature of space-time is what we perceive as gravity. So when we put test objects in this curved space-time, it's not that these objects are being pulled by a force, but rather they are traveling along bent or curved trajectories because the rubber sheet or the sheet on which they are traveling is itself bent, is itself curved. So it's completely changed the notion of what we mean by gravity. And Newton taught us that gravity is a force, but Einstein's theory of general relativity, which we now know to be the right description of space-time and gravity, it tells us that gravity is not really a force. It's really a consequence of the curvature of space-time due to introducing matter and energy distributions. And that's basic content of general theory of relativity. If there are any questions, please do ask. So our theories of gravity, in particular, the general theory of relativity, have had tons of successes, and I just list a few of them. First, of course, Newtonian theory of gravity described how planets go around the sun. So it was a successful mathematical framework. It described precisely the orbits of different planets around the solar system. In the solar system, general relativity came along and actually explained that there are little bits and pieces in that motion, little bits and pieces in that motion. So there are little bits and pieces in that motion which cannot be explained by Newtonian mechanics. And one of the great successes of Einstein's theory of general relativity was that the small deviations that you could see from observations, small deviations that you could see from Newtonian mechanics could actually be accounted by Einstein's theory of general relativity. Now, there's a very nice question here from Tom saying, I've been taught that gravity is one of the 4 fundamental forces. Why is this so if it is not actually a force? Excellent question. And we will reserve the answer to that at the end of the lecture, okay? So let's just go on with this for the moment. So understanding precision corrections to planetary motion, that was one of the first successes of the general theory of relativity. The other big success of the general theory of relativity is predicting that the universe underwent a Big Bang at its early stages. So the entire field of Big Bang cosmology, which tells us that as we look out there in the universe, we see that every part of the universe is expanding from every other part. And that is actually one of the predictions of Einstein's equations, a solution to Einstein's equations. And this is, of course, one of the most profound things that we know about nature, that when we look out there in the sky and we look at it with a radio telescope, we see the echoes of the Big Bang left over in the form of something called the cosmic microwave background radiation. It's a lot like radio static, but it's whichever direction you point your telescope in the night sky, your radio telescope in the night sky, you're going to detect this cosmic microwave background, which corresponds to a temperature of 2.7 kelvins, an incredibly cold temperature, which is the remnant of the hot stage of the early Big Bang universe, which then underwent expansion and the universe cooled down. And what we are left with as an echo of this hot Big Bang is this 2.7 Kelvin cosmic microwave background radiation. Here's a question that asked whether the mass of the object that causes the curvature of time, does it change? Not necessarily. The mass can be, so this question relates to the curvature of space-time brought about by introduction of a mass. So you can take the mass of an object, keep it completely fixed, and it will curve in a very precise way the space around it, and it will also curve the time around it in a very particular way. It's not something that we can think about very easily, but we can't visualize it, but we can use the tools of the mathematics, which is differential geometry, to understand what this curvature actually means. Now, the final great success of Einstein's general theory of relativity is prediction of the large-scale structure of the universe. Matter in the universe is distributed in some particular fashion, and if you look at the universe on very large scales, you see that the matter is distributed in this kind of form. In the picture here, you see filaments and various kinds of structures, and these structures have been analyzed in great detail, and we understand that Einstein's general theory of relativity and an understanding of gravity actually is consistent with these ideas of structure formation that are seen observationally. Another wonderful question: do photons warp space-time as they have energy? Absolutely. If you send light through space-time, well, light carries energy in the form of electromagnetic radiation. And so if you look at Einstein's equations, on the right-hand side, you feed in matter and energy. On the left-hand side, you get out curvature, okay? And this curvature is incredibly small if you just send out a beam of light, but it's nevertheless there. All right, good. So now I'll move on to the next slide. There's a number of very nice questions coming in, which I'll address at the end of the lecture. So one of the other great predictions of the general theory of relativity is something called gravitational time dilation, which is actually just another effect of the curvature of space-time. And so one of the amazing things, and this is a generalization of what Simon already talked about yesterday in the context of special relativity, what general relativity tells us is that time moves slower near heavy objects. This is an amazing thing because it tells us that if you have a clock near the surface of the Earth, and if you have a clock placed in a satellite far away, then time moves slower near the Earth than it does for the clock on the satellite far away. This has a very important technological application, and it's important for the proper functioning of our sat-navs, which utilizes the global positioning system. We can calculate very easily using one of these formulas that I've written here, which is one of the time dilation formulas in general relativity, which tells us exactly how time intervals change as you move far away from an object which has some given mass, capital M. And you can work out that a clock on a satellite, which is in a geosynchronous orbit, actually gains about 40 microseconds each day compared to a clock on the Earth. And which means that time is traveling faster up there near the satellite. And if we don't account for these time changes, then we're going to make mistakes in the triangulation procedure that we use to do GPS, global positioning. And the mistakes would be sufficiently big that, you would find yourself driving somewhere in Swansea, but actually the GPS might show you driving in Cardiff. So it's actually incredibly important to incorporate general relativistic corrections. I can explain later towards the end of the talk, I'll kind of give you a simple explanation for why time flows slower near heavy objects, if you're interested. Okay, so let me carry on. What else do we know about gravity from Einstein's equations? Well, one of the great predictions of Einstein's equations, which Einstein himself wasn't in a position to appreciate fully. In fact, he denied the existence of these things called gravitational waves when people predicted that his equations actually do predict gravitational waves. So Einstein's GR actually tells us that if we take a heavy object and shake it around, which means accelerate it, it's going to produce ripples in space-time. It's exactly the same way, as if you kick the surface of a pond, you're going to produce ripples that move outwards on the surface of the pond. Or in Maxwell's equations, electricity and magnetism, you take a charge. We all know that a static charge produces electric fields. If you take the charge and shake it really vigorously, you'll produce both electric and magnetic fields because a moving charge is a current. And if you work it out using Maxwell's equations, you will see that the charge actually, an accelerated charge actually radiates energy. It radiates electromagnetic waves, which we call light. So in exactly the same way, if you take a mass and you shake it around, you're going to produce gravitational waves with ripples of space-time. And this prediction was checked and confirmed remarkably in 2016 by these amazing experiments done by the LIGO collaborations, where what they did in 2015, and since then, they've actually detected about 20 such events. They're extremely violent events, and they involve the merger of extremely massive objects called black holes. And we're going to talk about black holes in a little bit. Before we talk about what black holes are, let me actually say how powerful these mergers are. These black hole mergers involve pairs of black holes, which are kind of in a binary system, and they just happen to get so close to each other that they spiral inwards and they coalesce. This process is extremely violent. It occurs on a time scale on the order of a few milliseconds, and the black holes themselves are objects whose masses are much bigger than the mass of the sun itself. And we'll see that in the next slide. And so this dance of these two objects, which merge in this violent spiral, which we call the black hole merger, produces a burst of gravitational waves, a burst of energy released in the form of gravitational waves. And these gravitational waves you can work out, and I'll sketch this in the next slide. They produce a power during that short time scale, a power on the order of 10 to the 49 watts. It's a huge power because it's actually bigger than all the power generated by all the luminous stars in the universe. So these are extremely spectacular events which you cannot see optically, but you can see their effect via gravitational waves, which as they pass through us, they actually curve the space-time around us as they pass through us. And that was the effect that was detected by the LIGO collaboration. So here, I always thought that it's a nice it's nice to do a little bit of an exercise here. And the slide looks a little bit busy, but those of you who are really interested can, after the talk, go through these slides. I think we'll make them available, and you can look through this little calculation. So this is basically what happened in the first event detected by the LIGO collaboration. Two black holes, let's call them black hole 1 and black hole 2. Black hole 1 has a mass of 36 times m solar. So that little symbol there tells us that m with a dot below it is the mass of the sun. So M1, which is black hole 1, had a mass 36 times the solar mass. M2 had a mass on the order of 29 times the solar mass. These two coalesced, okay? They spiraled and coalesced to produce black hole 3, which has a mass of about 62 solar masses. And there's a deficit in the mass, you will see, and this deficit is radiated in gravitational waves. What's really going on here is actually a manifestation of what all of us have heard about at some point, Einstein's famous equation, E equals mc squared. Here, the rest mass energy in the black holes is being converted into gravitational waves. And we can figure out exactly how much energy is being emitted in this process. So the energy released is the sum of the masses of the two objects that went to make this merger minus the mass of the object that was formed at the end. So that's 36 plus 29 minus 62 times the solar mass times c squared. Unless if you put the numbers in there, these are astronomical numbers. These are numbers that we can't even imagine. So the total energy emitted during this merger process is 5.4 times 10 to the 47 joules. Huge number. This is basically 3 times the rest mass energy contained in the entire sun. And that energy was emitted in a few milliseconds. So you can take this energy and divide it by the time in which it was emitted, which is a few milliseconds, and you discover that the power carried by these gravitational waves was 10 to the power 50 watts. Astronomical. Well, astronomical is actually a word that doesn't do it justice, because if you calculate the power of all luminous stars in the universe, each star, like the sun, has a power of about 10 to the 26 watts. Again, it's a number which we can't really imagine. Multiply that by the number of galaxies in the universe, that's 10 to the 12. Multiply by the number of stars in each galaxy, that's 10 to the power 11, and you get 10 to the 49 watts. So these black hole mergers were producing more power in gravitational waves than all the power produced by all the luminous stars in the universe. It's amazing. And we've seen 20 of these events, and they all confirm our understanding of gravity based on Einstein's equations. It's absolutely remarkable. So now let's come to the first little thing in the heading of this talk, which is black holes. So let's first say a few things about black holes. You see, black holes were not first seen astronomically. They were not seen out there with any telescopes. They were first a prediction of Einstein's equations. Another point that I want to emphasize, that what we're seeing with Einstein, and also with Newton, but actually more so with Einstein, is we are using basically pure thought and mathematics to explain what the universe is. Einstein wrote his equations down based purely on mathematical consistency and thought experiments. Okay, they were not based on observations. They actually made predictions which were then confirmed when people went out there. Same thing here. Carl Schwarzschild, a mathematician who was out there in the trenches in World War I, thought that one way to take his mind off the stresses of being in the trenches in World War I would be to take Einstein's newly found equations and try to find solutions to them. And that's exactly what Carl Schwarzschild did. he found these beautiful solutions, the simplest possible solutions to Einstein's horrendously complicated equations. And these solutions were made possible because Schwarzschild assumed, let's take the space-time to be spherically symmetric. Let's see what kind of solution we get. And Schwarzschild got this solution, which we now call a black hole, a term which was originally coined by John Wheeler in 1967. So what are black holes? First, I'll just say roughly speaking, what black holes are. The black hole solution found by Schwarzschild is actually a description of a space-time which has spherical symmetry in it, which means that if you rotate around it, the space-time looks the same. Okay, it just describes geometry. It kind of describes a curved geometry, and it's characterized by a very important quantity that I will keep talking about. It's called the Schwarzschild radius. Now, what is the Schwarzschild radius? Well, the Schwarzschild radius is the radius of a very special sphere in this geometry, which is called the event horizon. Okay, and now I'll tell you what the event horizon is. The event horizon is, you can think of it like a one-way membrane. Okay, it's this imaginary sphere that you can draw in space centered around some point, and it has a special property that anything that happens to fall across or fall through the event horizon is lost forever. In other words, it can never emerge on the other side. So the event horizon is like a one-way membrane. So if I fall into the black hole, I wouldn't actually know that I've crossed the event horizon, but I would never be able to emerge out of the clutches of the black hole. And so the event horizon is one of these mythical boundaries. It's one of these regions from which light itself cannot escape. And that's why the black hole is called a black hole, because no light that's emitted from inside the black hole can ever make it out of the horizon. So black holes are black, and that's why we call them black holes. Okay, the radius of this event horizon which is called Schwarzschild radius, is proportional to the mass of the object, or the mass of the black hole itself, or the mass of the object that went into making the black hole. It's proportional to Newton's constant divided by the speed of light squared. An idea of how big or how small black holes are, you can get by actually plugging in different values of masses here. So if you took a black hole, which happened to, for example, have a mass of the Earth, you would find that the Schwarzschild radius of the black hole was just about a few millimeters. If you imagine that the black hole has a mass of the sun, then you would find that the Schwarzschild radius is about 1.5 kilometers. So black holes are basically incredibly dense objects. Okay, it's one way to think about them, that they must have been formed by taking in some heavy object, an astrophysical object, and which got compressed into a region which was incredibly tiny. Imagine the mass of the Earth compressed into a region which has radius 4 millimeters across. That's unbelievable. Or the mass of the sun compressed into a region which has a radius 1.5 kilometers. So again, this is something that we can't wrap our heads around, but such astrophysical objects exist. In fact, black holes, as is well known, are formed by collapsing stars. So if you have very heavy stars a few times the mass of the sun, our own sun would never collapse to form a black hole. It would have a much more boring end. But if your star is much more massive than the sun, 7 or 8 times more massive than the sun, then what will happen is, as the nuclear fuel inside the sun burns out and it's no longer able to support itself against its own weight, the entire matter in that star will just simply collapse in on itself. Eventually, the collapse will be so drastic that no force can prevent the collapse, and you will get an object which is smaller than the Schwarzschild radius associated to the mass of that object, and that's what we would call a black hole. So the collapse of massive stars yields black holes. So if you are an observer sitting very close to a heavy, massive star undergoing gravitational collapse, like so, in the end, you would find that the gravitational forces at some point, when the object becomes so dense, the gravitational forces are so strong that the gravitational force at the location of your foot is actually much bigger than the gravitational force at the top of your head, and you would experience these tidal forces that would stretch you apart, which is more or less what this figure is trying to show. And eventually this object would shrink to a radius which is smaller than the Schwarzschild radius, and you would end up with a black hole. That's kind of what's illustrated in this photograph here. This is a picture of a star in a particular constellation, and here's a picture of that star in 2007. And here's the same picture of the same region in 2015. The stars disappeared. And this is believed to be a star that has collapsed to form a black hole. We know from astrophysical observations that this star here, which was visible in 2007, had a mass on the order of 25 solar masses. It's kind of interesting to learn how you could even calculate those masses or estimate those masses. So point is that as you have matter which collapses, and this collapsing matter crosses this Schwarzschild radius, you end up with a black hole. What happens to the matter that keeps falling through the event horizon? Well, eventually it ends up at a point that we call, or a region that we call the singularity. The singularity is basically where Einstein's equations break down, because the curvature of space-time becomes so large that you get nonsensical expressions. If you try to use them, curvature of space-time becomes infinite. And so something else has to come around and replace Einstein's equations there. Most likely it's going to be something that's quantum mechanical in nature, because the singularity is a region which is a very tiny region, point-like region in space-time. And so we're talking about very short distance physics. And so it's very likely that the quantum nature of gravity will become very important if you want to understand what happens at the singularity. Okay, so I've said a few things, lots of things about black holes. Anybody have questions, please, about black holes? Please feel free to ask. Wow, there's tons of questions. So there's tons of questions which I will address towards the end. Here's an interesting question: is there a lower limit for a mass of a star to collapse to form a black hole? Yes, there is. The actual limit on the mass of a star to collapse and form a black hole is in contention, because it depends upon a variety of things. It depends upon the equation of state of the matter that goes into forming these heavy astrophysical objects. But we can roughly say that any star which has a mass above, say, 5 or 6 solar masses, maybe even 7 or 8, is more likely to collapse and form a black hole. Okay. So let me move on to the next slide. This is again to drive home the fact that black holes are not a figment of our imagination. They're not some abstruse solutions to Einstein's equations, which have no reality to them. Here is the most amazing black hole of all. This is an animation. Look at this picture. If you haven't seen this before, this is one of the most amazing animations you can ever see. Okay, so what is this? This is actually not an animation. It's not a computer animation. This is actually a snapshot. This is actually a set of snapshots, or a sequence of snapshots of the positions of stars at the center of the Milky Way, or our own galaxy. And all these snapshots have been put together and made to form this little movie. And so this movie basically traces the locations of a large number of stars near the center of the Milky Way, okay, over a period of about 20 years, from 1995 to 2016. And let me show you again what they are doing. They're all going around something, right? And that something is out there. It's marked by that asterisk. All these stars are going around something which you can't see, okay? So you can, by looking at the trajectory of these incredibly massive stars, some of which are several times the mass of the sun, and it's worth actually pointing out that one of these guys, actually this particular star, which is going through this hairpin bend, right? It gets to a velocity very close to half the speed of light when it's very, very close to this edge where it's executing the hairpin bend. So these things are being accelerated to immense velocities by something which we cannot see. By looking at the orbits of these stars, you can actually deduce from the velocities and the orbits, you can deduce the mass of the objects that's pulling them, that's causing them to orbit around it. And the mass of this object is about 4 times 10 to the 6 solar masses. That's 4 million times the mass of the sun. You can also calculate how big the region is where this mass must be based on how big these orbits are or how small these orbits are. And we can say with confidence that all this mass, 4 million solar masses, is concentrated in a region which is much smaller than the Schwarzschild radius associated that we would write down for a black hole. And so that tells us that what's going on there is actually, there is a supermassive black hole at the center of our galaxy. And supermassive black holes seem to exist in almost all galaxies, and they play some very important role in galaxy formation. So that's something that our astrophysics friends can tell us more about. I know very little about what role these black holes play in the formation of our galaxy. But they exist, and this is one of the most amazing confirmations of that. Now let's move to the more kind of the theoretical aspect, which is what I want to talk about, which is where, physics progresses by building up contradictions. All the great revolutions in physics, like quantum mechanics, relativity, they all happened because there was a contradiction between something or two things that were very well understood. Okay, quantum mechanics was a contradiction between thermodynamics, statistical mechanics, and something that we were trying, the properties of electromagnetic radiation. Relativity was an outcome of a contradiction between Maxwell's equations that describe electricity and magnetism, and if you wish, Newtonian laws of mechanics. So every time there's a conflict in physics, something amazing, something new happens through that churn. There's a period of great confusion, and these conflicts are always coming out of theory, which means out of the mathematics. So here I'll very briefly on this slide just summarize to you what that conflict is. It's very difficult for me to get across what the conflict is without mathematics, but this is a friendly talk for students, and so I will just explain what this contradiction is. So Einstein's equations tell us that all black holes look the same. Pack enough mass m into a region which is smaller than the Schwarzschild radius, and lo and presto, you're going to get a black hole. Einstein's equations, if you solve them and do all sorts of things to their solutions, you take mass distributions that are not spherical, you put sharp points on your mass distributions and let them collapse to form a black hole. The point is, Einstein's equations, no matter what mass distribution you start with, Einstein's equations tell you that the end point of gravitational collapse, black holes, they are featureless. They don't care what went into making them. And this is a very important theorem which you can prove mathematically. Sounds very funny. It's called the no-hair theorem. The fact that black holes have no features is something that physicists like to call the no-hair theorem, which basically states simply that black holes have no hair. That's what this picture shows. Okay, what they're only characterized by is their mass, their angular momentum. The objects that went into making a black hole might have been spinning before they collapsed, and there is angular momentum conservation, and so black holes might carry some angular momentum. If it so happens that the matter distribution had a charge on it, then the resulting black hole would also carry that charge. So if you tell me what the mass is, what this angular momentum is, and what the charge is, you pretty much have nailed down the black hole. There is no difference between black hole A and black hole B. It doesn't matter if you took black hole A and formed black hole A out of a whole bunch of television sets thrown together, another black hole formed out of cars thrown together. The end product wouldn't be able to tell what went into making it. This is all very nice, and it's fantastic to think about this in classical mechanics. And I've talked about general relativity and special relativity, one of the great pillars of modern physics, our understanding of physics. The other great pillar is quantum mechanics, which I'm not going to talk about. But that great pillar of physics, which is being tested for 100 years, underlies all our technologies today. That other pillar of quantum mechanics actually tells us that information loss simply cannot occur. Okay, quantum mechanics forbids loss of information. General relativity tells us that black hole formation is accompanied by loss of information because you've lost the information of what you threw into a black hole, because black holes are featureless. Quantum mechanics says that cannot happen. Okay, so here is a clash between the two titans of physics, general relativity and quantum mechanics. And so there's a great contradiction, and physicists recognize opportunity when there is contradiction, and so have devoted their energies to understanding this contradiction for the last 40 to 50 years. And this resolution, although it's not completely resolved, there are now glimpses of this resolution, and the glimpses of this resolution provide us with a glimpse of a complete revolution in our understanding of space-time and quantum mechanics. So I'll just kind of want to walk you through that. So here's the first amazing thing that happens when you mix black holes with quantum mechanics. So quantum mechanics forbids loss of information. That means that black holes, if quantum mechanics is right, which we know it is right, then something has to happen to black holes. Black holes must not be, this no-hair theorem for black holes must not be true if you bring quantum mechanics into the game. This is what Stephen Hawking, one of the great physicists of our time, wanted to understand. So he put black hole physics, which is Einstein's general theory of relativity, and put it together with quantum mechanics and tried to see what would happen. And he did a very famous calculation, a very important calculation, and a very hard calculation in a very beautiful paper, a seminal paper, and he could prove that black holes are actually not black. When you include the effect of quantum mechanics, there is a very tiny, subtle effect due to quantum mechanics, which we can understand using this cartoonish depiction here. And I stress this is only a cartoonish depiction. What this cartoonish depiction says is that if you use the effects of quantum mechanics or include the effects of quantum mechanics, empty space is not really empty. It's really a frothing soup of virtual particles that appear and disappear. Okay? And so you get particle-antiparticle pairs, electron-positron pairs. You're going to hear about positrons tomorrow in Niels Matson's talk. So you're going to get electron-positron pairs being produced from the vacuum fleetingly. And every so often, one of the particles in this pair will have negative energy, will fall into the horizon, decreasing its mass, decreasing the mass of the black hole. The other, its partner, will be chucked out to infinity, and that's what we will see as something that we call Hawking radiation. So Hawking did this amazing calculation where he showed that black holes actually radiate energy just like all hot objects do. Here's a lump of hot coal, and we know that it glows. So black hole really is like a lump of hot coal if you include the effect of quantum mechanics into it. And it radiates energy. This radiation has a particular spectrum, which you will learn about as physics students. You will learn about in your first year or second year courses that the radiation emitted by a hot object has a very special spectrum, which is known as Planck's black body spectrum. Planck was one of the founding fathers of quantum mechanics. And it's remarkable. It was actually a bit of a miracle when Hawking did his calculation and discovered that the spectrum of radiation from a black hole is in fact the same as Planck's spectrum. So the radiation from a black hole is exactly like the radiation due to a hot object. And Hawking radiation, whenever you have radiation emitted by a hot object, this hot radiation carries with it something that in thermodynamics we call entropy. Okay, it's an abstract concept. Some of you would have encountered it. I'm going to say a few words about entropy in a bit. What the previous slide tells us is that because black holes radiate energy, they're losing energy because some energy is coming out of them, right? And this energy means that black holes, this energy radiated, according to Hawking, means that black holes slowly evaporate away. Okay, so theoretically, what we would say is that black holes, when quantum effects are included, are not black, they're radiating energy. As they're radiating energy, they evaporate away. The process is very, very slow because if you look at Hawking's formula for the temperature, there's all these amazing constants of nature. Planck's constant, the speed of light, Newton's constant, something called Boltzmann's constant. But Hawking temperature is proportional to 1 over the mass of the object that went into making it. okay, went into making the black hole. And if you put all the numbers together, you see that Hawking temperature is 6.17 times 10 to the minus 8 kelvins times the solar mass divided by the mass of the black hole, which means that if the mass of the black hole is on the order of the mass of the sun itself, the Hawking temperature is 10 to the minus 8 kelvins. It's an incredibly tiny temperature. It's such a small temperature that the cosmic microwave background, which is at 2.7 kelvins, very close to absolute zero, will actually swamp any effect of Hawking temperature. So it's not something that we can see observationally, okay, from astrophysical black holes. If the black holes we are interested in are incredibly small and can be produced in a lab, so the mass here is very small, then the Hawking temperature would be big and we would be able to see Hawking radiation coming from microscopic black holes, which have small masses. Astrophysical black holes, they Hawking radiate, but the process is incredibly slow. Now, as theorists, we don't care that this process is slow. What's important is that it happens. And what it means is that, look, we threw stuff into the black hole. Just maybe, if we collect all the Hawking radiation coming from the black hole, wait till the end of time and collect all the Hawking radiations coming from the black hole, we might be able to reconstruct all the information of what we threw in by actually studying the Hawking radiation. This is the idea that all people who believe quantum mechanics is correct have had for a long, long time. And whether this happens or not, we don't know. In fact, we are getting just as of the last 4 or 5 months, the field of black hole physics and quantum mechanics has converged on a possible solution to this paradox, which is called the information loss paradox. I'm not going to talk about this, but this paradox of information loss in classical black holes and how that's not allowed by quantum mechanics, this is the famous information loss paradox. Now, let me talk a little bit about entropy, right? I mentioned entropy. What is entropy? Well, everybody who has learned a bit of thermodynamics at some point might have encountered this idea called entropy. It's really abstract. What entropy really is, often people say entropy is a measure of the disorder of the system. If you take a piece of ice, which can be thought of as a crystal of atoms or molecules, you heat it up, you turn it into water, you've created a disordered phase. And in the process, what happens is that the entropy of the system increases. So for people who are interested in a more fancy definition, which you will learn about as physics students, you will learn when you learn statistical mechanics, that entropy is something that actually counts the number of possible states of the microscopic constituents of your system. So it tells you how many possible ways you can arrange the atoms and molecules in your system, given, say, the energy of the system fixed. So the entropy is really telling you something about the microscopic details of your system. This is exactly what you need, you see. If you made a black hole out of something and you've lost the information of what that something was, that means you've lost a certain amount of information, you've lost a certain amount of microscopic details. The entropy quantifies exactly how much you've lost. Okay, so there's a very precise definition of entropy. In fact, here we will borrow terminology from computer science. The entropy is precisely the number of bits of data, the number of zeros and ones that you need to give to reconstruct the full system. And for most physical systems, any gas in the room that you're sitting in, the entropy is always proportional to the volume. This is something you will learn in your first course on thermodynamics, which you will encounter in your first year. You will learn that entropy is always proportional to the volume. That's what you think. Black holes, amazingly, have entropy. And this was another celebrated result due to Stephen Hawking and Jacob Bekenstein. Black holes have thermodynamics associated to them. You see, black holes were all about geometry of space-time, and for all of you who've been following me so long, you will be scratching your heads. Where did thermodynamics come out of this? You know, we solved Einstein's equations. Einstein's equations told us about geometry of space-time. Now you're telling me that there's this thing called a black hole, and you're talking about thermodynamics. You're talking about things that we usually associate to gases, hot lumps of coal. Where did that come from? So this is at the heart of the mystery of the structure of space and time, that somehow gravity and space-time seem to know about thermodynamics. Okay, so this is what Einstein or Stephen Hawking and Jacob Bekenstein found, that black holes actually have an entropy. And this entropy, even more remarkably, is not proportional to the volume of this black hole. It's actually proportional to the area of the horizon of the black hole. It's an amazing thing. And Hawking proved this theorem, which is called the area theorem, that if you, no matter what you do to a black hole, you subject it to any kind of physical processes, the area of the horizon of the black hole will always increase. So if you take two black holes and merge them together to form a new black hole, like the black hole mergers we spoke about right at the start, the new black hole had better have an area which is, or horizon area, which is bigger than the sum of the areas of the first two black holes. And that in fact, certainly, that's in fact confirmed in one of these black hole merger events that was seen by LIGO. So Hawking's area theorem tells us that the area of the horizon of the black hole can never decrease. It can only increase, okay, or remain the same. And that is exactly the property that entropy in thermodynamics has. So it's remarkable. And so Bekenstein and Hawking together proposed, actually independently proposed, the same formula for the entropy of a black hole. And it's proportional to all these wonderful constants of nature, and it's proportional to A, which is the area of the horizon of the black hole. This equation, by the way, finds its way onto a stamp or a coin. I can't remember which one. But it's one of the most beautiful equations in nature because it contains all the fundamental constants of nature in one place. It's really remarkable. So what does black hole entropy tell us? Well, what black hole entropy does is it actually counts something. So the way you have to think about it is, if you imagine that the surface of the black hole horizon is actually split up into tiny little cells. Each cell, the size of something that I call the Planck area. The Planck area, by the way, is precisely these constants that appear in front of the black in the Bekenstein-Hawking formula, c cubed over gh bar. So that quantifies something called the Planck area. It's the smallest possible unit of area known in physics. It's 10 to the power minus 70 square meters. So if you take, little pieces of this area, 10 to the minus 70 square meters across, and paste them on the horizon, you'll get a tiling of the horizon. You count how many of these little pieces you've got, pieces of tile you've got, and that tells you the entropy of the black hole. That tells you how many bits of data you need to reconstruct the information inside the black hole. This is an amazing thing because it's telling us that in some way, all the information of what went into making the black hole is actually encoded in some way on the horizon, on the surface of the black hole. There's a very nice physical or intuitive picture for why this might be true. And I'll probably leave that to the end when we have some questions about this. So, but this is precisely the second part of the title of my talk, holography. You see, holography is the word that is used to describe holograms, the creation of holograms. Holograms, if you remember, are basically three-dimensional images of real objects that we create. And the information on these three-dimensional images is usually encoded in a two-dimensional surface, some kind of a screen. And you can reconstruct the three-dimensional image by passing beams of light or lasers through this two-dimensional thing on the holographic screen. So holography is a general word where you have information about a higher dimensional system encoded in a lower dimensional system. That's exactly what's happening in gravity. All the information of what's inside the black hole is actually encoded on the horizon. So gravity is telling us that the holography, space-time and gravity, our Einstein's equations of black hole physics are telling us that gravity obeys a certain kind of holography. Exactly how this information is encoded is one of the big questions, okay? So the big questions, how is this holographic information encoded? If I could read this, is there some way to read this information which is on the horizon of the black hole and tell what is happening inside the black hole? What's the resolution of the information loss paradox, which I spoke about earlier? How do you retrieve the information that went into the black hole? These are some of the big questions that have been driving this subject. And let me just leave you with a couple of answers. And we already have answers to the first question. How is this holographic information encoded? This comes from this other amazing mathematical structure that we physicists work with, which is called string theory, one of the candidate theories of gravity. And what string theory tells us is that if you have a system which gravitates and you keep it inside a box, and you can think of this gravitation system as a black hole, you can show that this gravitational physics inside the box emerges from quantum mechanics of some kind that lives on the walls of this box. So there is holography taking place, and you can show this very precisely in many, many examples. And what string theory and realization of holography in many, many examples today tells us is that the ripples of space-time near black hole horizons, which contain the information about what's inside the black hole, is entirely described by a completely different system that you thought had nothing to do with black holes. This is the physics of quarks and gluons, the quantum mechanics of quarks and gluons, the kinds of particles that make up nuclei, okay, neutrons and protons, strong physics of strong interactions and strong nuclear force. It turns out that the physics of gravity is actually in disguise the quantum mechanics of quarks and gluons in one dimension lower. This is an amazing realization, and it's driven the entire subject of particle physics and theoretical particle physics heavily in the last 20 years. And one of the great drivers of this realization has been that hard problems on one side, so you can think of this as, you know, two different branches of physics. One is black hole physics and gravity. On the other side, we have the physics of quarks and gluons. They both have their hard questions and easy questions. One of the remarkable things of the mathematical equivalence between these two is that hard problems on one side get translated into easy problems on the other. So anything that you found hard to calculate in the physics of quarks and gluons, you could find an answer to it easily by studying properties of black holes, and vice versa. So it's really amazing. And this is the kind of research that has tied the entire particle theory group in Swansea together. So that's a bunch of us at the top who work on string theory, quantum field theory, and black hole physics. And at the bottom, we have people who you've heard from Simon Hands yesterday, who work on the physics of quarks and gluons. And so we are basically two different fields, but holography bridges us, and we can talk to each other. Black hole physicists and string theorists can talk to people doing physics of quarks and gluons. And we have cosmologists studying other aspects of gravity in Swansea, which is the particle physics theory group. Tomorrow, you're going to learn from Niels Madsen the physics of antimatter, which is the other big group or effort in Swansea doing experimental physics. But I'll just close with this final slide. I think I've gone a bit over time, but this kind of summarizes the state of affairs in this very exciting field of black hole physics, quantum gravity, and quantum mechanics. So now I guess we have to take all the questions in turn. I think I should just end there. Thank you very much, everybody, for your attention.
Thank you very much, Prem. I've been looking at the questions, but I think these require an expert to answer. So
Shall we take them from the beginning? I'm happy to take most of them on. And
I think I have to leave that to your discretion. There's a number which are vaguely similar, so I think you don't need to answer every single one.
Yes. Okay. So I'll take, say, the first one, which is which I promised to answer at the end. The first one was, I've been taught that gravity is one of the 4 fundamental forces. Why is this so if it is not actually a force? Okay, so the term force is a very loose. It's, you know, we are using the English language to describe a physical phenomenon. So what we really mean by a force is some kind of interaction between things. So our classical description of gravity, due to Einstein, is actually telling us that gravity is not best thought of as an interaction between things, but is actually best thought of as one object curving the space-time geometry around it, and another object reacting to that curvature of the geometry. So there is interaction, but the thing that's mediating the interaction is actually the space-time itself. So in that sense, I would say this is not a conventional force, but it's more like an interaction mediated through geometry. So here we are basically arguing over semantics, but you can probably understand through my answer exactly what I'm trying to convey. Okay, next question. Does the mass of the object cause the curvature of time that causes the curvature of time? Does it change? I think I already answered this question. Do photons warp space-time since they have energy? Absolutely. Anything that has energy will warp space-time. If the energy density is incredibly small, the warping will be too small to observe, but anything and everything will warp space-time around it. How did they get the photograph of the structure formation? That's a fantastic question. So the photograph that I flashed was actually not a photograph. It was actually the result of a simulation on a computer. Okay, and what they do is they produce all these simulations of many bodies. These are called n-body or multi-body simulations on computers, subject to the rules of gravity and other interactions that take place between them over a period of time. And then they compare that resulting structure with the distribution of matter, the large-scale matter that you can see in today's universe. And that, of course, relies on very detailed astrophysical observations. And there is significant agreement between the observations and the predictions from these computer models. Next question, as cosmic microwave background is present in the universe because gamma rays from the Big Bang were elongated, does that mean at one point the universe was completely full of visible light? Very good question. So this question is asking, basically, I'll give you the answer straight away. The question asks, well, the universe, the microwave background radiation that we see today consists of radiation that's largely microwave. So microwave radiation has wavelengths on the order of millimeters, I think. So what's really happened during the course of the evolution of the universe is that the very early universe was incredibly hot. The temperatures were so high that the typical radiation that was being exchanged by the soup of matter in the universe, the hot matter in the universe, was actually radiation which had wavelengths of the order of gamma rays, okay, or even higher. But as the universe cooled, it's like a gas cooling. The temperature of the gas cools, and therefore the wavelengths of the radiation, the frequencies of the radiations go down that are being exchanged by this hot soup of particles. And as the frequencies go down, the wavelengths increase. And so you get a movement from, gamma rays towards visible light, then towards infrared, then towards microwave. So indeed, at some point, the universe was completely full of visible light, if you wish. How does the bending of space-time relate to how gravity affects the acceleration towards the center of the Earth? Well, the bending of space-time is literally what causes the what we call the acceleration towards the Earth. And of course, as you get closer towards the center of the Earth, if we could avoid all the rocks and stuff, all the annoying rocks and stuff, if you could get closer and closer to the center of the Earth, the curvature of space-time would increase, provided the mass contained mass distribution, the total mass we're talking about is the same. The curvature of space-time would increase, and that would mean effectively the acceleration is larger. I hope that answers the question. The picture of cosmic microwave background radiation shows an irregular distribution. How could that happen? Why isn't the matter distributed evenly? This is a profound question, an absolutely brilliant question. This question has driven the entire field of cosmology. So this question is asking, in that picture that I flashed, I don't want to go back now because we are way over time, I think. So in that picture which I flashed, the snapshot of the cosmic microwave background radiation did not have the same color scheme. It had blues and yellows and reds. What that indicates is actually very tiny fluctuations in the temperature of the cosmic microwave background, not exactly 2.7 kelvins, but a small deviation. Each of those deviations is actually 1 part in 10 to the 6, okay? So it's 1 part in a million. So if you look at the night sky, or well, whichever part of the sky in one direction and move, look in completely the different direction, you're going to see the same microwave background radiation with the same temperature, but with a tiny fluctuation, which is 1 part in a million, okay? It's a very important question to understand. So that's actually very even. But there is a very important story in those fluctuations. Those fluctuations, we now understand, are a result of quantum fluctuations in our early universe. It's precisely those fluctuations that set the seeds for structure formation in the universe after the Big Bang phase was over. So what those tiny fluctuations you see in this cosmic microwave background represent are basically the seeds of what led to the structure-filled universe today. So those fluctuations are very tiny, right? But they are very important. And another question which is another very important question which is implied in your question is why, well, there is another big puzzle, why this temperature is so uniform across the night sky. We'll leave that for some other time. There's another question, sorry, what is space-time? Is it the same as what we perceive as time on Earth? Good question. What I hope I've tried to convey to you with these examples of gravitational time dilation, etc., is that the notion of time is relative. There is no such thing as absolute time. So what you call 1 second on Earth is not going to be the same as 1 second for a clock sitting on the geostationary orbit out there. So so the notion of time, the notion of space, how big is a time interval, how big is a spatial interval, these are all relative, okay? But what general relativity tells us is exactly how these definitions of time intervals and spatial intervals are related in different points of a curved space-time. It's dictated by gravity and by Einstein's equations. Have any man-made objects ever gone into a black hole? Well, the answer to that is a resounding no, because the closest black holes that we have seen are so incredibly far away, right? They're so incredibly far away, like the black hole mergers that we've been talking about that were observed by the LIGO experiment. Those black hole mergers happened 2 billion years ago. So those were black holes that were, well, at the very least, they're hundreds of millions of light years away. So there's no way we could send anything that far. The black hole at the center of the Milky Way galaxy, again, hundreds of thousands of light years away. So we won't be able to have done any experiments with those things. Oh, here's a question which is a science fiction question. If being close to a heavy object causes time to travel slower for you, meaning you age more slowly, could you slow aging even more by accelerating quickly around the object? This is an absolutely great question. You've actually hit upon what drove Einstein to the general theory of relativity. Okay, I'm going to defer answering to this question because this is a very deep question. It lies at the heart of general relativity. It's called the equivalence principle. And I'll just summarize the answer by saying that this was indeed one of the deep insights of Einstein, that an observer inside an accelerating rocket ship could tell, you can't tell the difference between an accelerating reference frame or an accelerating rocket ship and the effect of gravity. The two are essentially the same. So yes, if you are accelerating in a rocket ship, you will experience time dilation with respect to an observer who is not accelerating. Let's see, these are like tons more questions. Another question says, you mentioned earlier that signals cannot travel faster than light, but what of quantum entanglement? I've heard multiple times before of experiments where the state of a system of two entangled particles has collapsed seemingly instantaneously. What are your thoughts on this? Absolutely pertinent question, and I want to actually, it's very good that you brought this up. This is actually absolute nonsense which is bandied about, that quantum entanglement you find written in lots of popular articles, including articles by people who should know much better, who claim that quantum entanglement actually involves transmitting signals faster than light. Absolute gobbledygook. Quantum entanglement does not involve transmission of signals faster than light. You cannot transmit any information between two entangled particles. The notion of the collapse of the wave function is actually a fictitious notion. We can talk about this later and I can give a text answer to you to you later. James, these questions will be stored, right? So I can give an answer.
Yes, definitely.
Yeah. Okay. Here's a question that says, how does 36m plus 29m equal 62m? Well, the answer is it doesn't. 36 plus 29 is 65. And so 65 minus 62 is the 3 solar masses of rest mass energy that got radiated. Where do the approximations for the number of galaxies in the universe and stars come from? They come from observations. Okay, so these are based on our observations and estimates of the number of stars, typical number of stars in Milky Way and all other galaxies that we can see around us. And by now we have pretty good estimates of the number of galaxies in the visible universe and the number of stars in every galaxy. Is it possible to take a photograph of a black hole? Well, not really, except two things. You can take a photograph of stuff that's behind the black hole, because black holes curve space and time. So if you have visible objects behind them, then the light rays emitted by the objects behind the black hole would actually be curved by the space-time geometry around the black hole, and you would see a lensing effect. So this gravitational lensing due to heavy objects like black holes is like a smoking gun signal for whether black holes are present or other massive objects are present. Another remarkable thing that you could do is what was done exactly a year ago. People took a photograph of the black hole horizon. What they actually did is take a photograph of essentially what I'm describing, of luminous matter as it is encircling and falling into the black hole. It creates a kind of a halo, and this halo also gets warped because of the space-time around it, and it produces these beautiful pictures that you see in this movie Interstellar, right? And this kind of picture is what was captured last year. So you can kind of see a picture of the space-time curvature around the black hole. I wouldn't call that a picture of the black hole, but I would call that an image of the effect of space-time curvature around the black hole. Okay. Can we try to harvest the energy from gravitational waves? Not really, because these black hole mergers that occur, they occur so far away, and we get to see only a very, very tiny bit of that power. So we get a very minuscule amount of that power which is actually emitted. Yes, of course, if we could sort of find some magic way to collide black holes at will and capture all the gravitational power coming from them, then of course they would be an enormous source of power. Right, so have I myself done much research on the other side of the black hole? Well, this is, yes, that's probably a question that I can answer later. Good, this is a very good question. Does this mean that all objects with mass have a Schwarzschild radius, but that the Schwarzschild radius would reside within the object? Bang on, exactly. Any object with a mass has a Schwarzschild radius, which is of course an imaginary radius. It can sit within the object, like the Earth has a Schwarzschild radius. But if you take the mass of the Earth and manage to squish it within the Schwarzschild radius, then it would form a black hole. Okay. Is there a lower limit for the mass of a star? If black holes are extremely dense, what happens to the matter that is condensed this much? Oh, very, very good question. There's a question from somebody asking, if black holes are so extremely dense, what happens to the matter that is condensed so much? Could quarks fuse to form heavier quarks, like with strange quarks and neutron stars? So that's an excellent question. As stars undergo collapse, they can form successively compact states of matter. So like you've already mentioned, when a solar mass star undergoes kind of collapse, it doesn't form a black hole. It leaves behind something called a white dwarf, which is actually just what we call it's matter which is mostly electrons. Okay, it's an electron gas with lots of carbon nuclei floating around. That's what a white dwarf is. If you put more mass on the white dwarf will collapse, but eventually it will collapse. The collapse will be halted, and it would form what you could call a neutron star, where a neutron star is basically made just of neutrons, which is in some sense the densest possible state of matter that we know, because it's the same density as density of nuclear matter. But then if you added more matter on top of a neutron star, then that wouldn't be able to, resist gravitational collapse. It could, in principle, form something that we call quark star, okay, which is a star made mostly of quarks, which are the constituents of neutrons and protons. But then you could ask, hey, what happens if you put more mass onto it? And then I think what happens if you put more mass onto it is that eventually no equation of state of ordinary matter that you could envisage can stop the collapse. So gravitational collapse will beat everything at some point if you add sufficiently large mass. That's something that you can kind of prove by one of these black hole theorems. Okay, don't event horizons have entropy due to Hawking radiation? That's a question. Does angular momentum of black holes affect how it behaves? Here's a question asking, how would angular momentum of a black hole affect how it behaves? In very, very interesting ways. Rotating black holes are called Kerr black holes as opposed to Schwarzschild black holes, which are non-rotating black holes. Kerr black holes have other very interesting properties. They actually have two kinds of horizons, and there's actually a way to harvest energy from the Kerr black hole, which is called the Penrose process. But that's for some other time. How can a black hole radiate energy if there is no way for energy to escape once it is beyond the event horizon? Precisely. So that was precisely the point, that the black hole is black as long as you think of the world as a classical world. But the world is not classical. The rules of quantum mechanics reign supreme. And so once you bring quantum mechanics into the game, you discover that black holes are not really completely black. They have a tiny amount of radiation that they emit. So your classical reasoning is invalidated by quantum effects. The quantum effects are very small nevertheless. Why is the positive mass object not sucked back into the black hole? This is a good question. It's a question about, okay, so there's a question asking, why isn't an object with positive energy sucked back into the black hole? So the way you should think about this, okay, people often say that black holes are like hoovers. They keep sucking matter in. That's not really true. Black holes are like any other star, right? The sun is a star. You might as well ask, why doesn't the sun hoover everything around it? And it doesn't, because the Earth has a kinetic energy, that it has a velocity which is tangential to its orbital motion. It is that kinetic energy which keeps Earth going around in an elliptical orbit around the sun and prevents the Earth from falling into the sun and being sucked in by it. Same thing would apply to a black hole. If you have an object which has sufficient energy that it can execute orbital motion around the black hole, it would continue to do so. If it had enough energy that it escape the gravitational pull of the black hole by having positive energy, then it can. So you can escape from the black hole, provided you start off at a point which is outside the event horizon. If you're on the wrong side of the event horizon, you can never get out. But if you're on the right side of the event horizon, you can get out. So here's, okay, there are these unbelievable questions, perfect questions. So here's a question that says, how do you know if a black hole actually takes in any information and isn't just kept on the horizon as time stops at the horizon? Okay, so this is a question that does need explanation. So I said that information seems to be locked on the horizon of the black hole. There are two ways to see this. One way to view the locking of information on the horizon of the black hole is from the point of view of an external observer. So imagine you're conducting this thought experiment where you throw something into a black hole. What actually happens is that as you throw this something into a black hole, well, as it approaches closer and closer to the horizon of the black hole, you see the object that's thrown into the black hole, the way you see it is by the light waves that it emits back to you. But as the object is getting closer and closer to the black hole, the light or the photon that's emitted by the object towards you is getting increasingly red-shifted because the light has to climb out of the potential well. In the process, it loses energy, it becomes redder and redder. So as an object falls towards the black hole, it becomes fainter and fainter, okay? It also gets stretched. But the point is, if you're an external observer, you will never see the object that you've thrown actually fall through the horizon. All you will see is that the object merges with the horizon, okay? And that's why an external observer would think that the information should be encoded somewhere on the horizon. But here's another way to see the same process. Imagine that you are the object going into the black hole. Einstein's theory of general relativity and whatever we know about black hole space-times and this thing called the equivalence principle tells us that if you are an object who chooses to jump into a black hole, you would find nothing special happening at the horizon. You would just fall in and keep falling in all the way until you hit the singularity of the black hole. So that means that from the point of view of the objects that are thrown in, they do make it way beyond the horizon and they do end up at the singularity. And therefore there are two complementary views. One where the object thrown in actually is inside the horizon of this black hole, the putative horizon, but also that the information of what's thrown in is stored outside the horizon. This is called black hole complementarity. It's one of these beautiful and actually very deep ideas in black hole physics. Kept people puzzled and scratching their heads for a very, very long time. Okay, so I think, it's been an hour and a half. Maybe what I should do is I should try to answer the remaining questions offline. Is that okay, James? Can I still do that, or?
That's absolutely fine. So we have email addresses for everybody through the registration. What we can do, if you'd like to prepare something in text addressing some of the questions that you feel need more of a considered answer, then we can do that. So there is a question whether or not this is being recorded. Yes, it is. And will we be able to watch it again later? That is the intention. We haven't done this before, but it seems to be working well. So the plan at the moment is that, yes, this in some form will be available to you, and we'll let you know that through email. Okay.
Okay. Thank you, everyone, for attending.
So I think with that we're done. Okay. Thank you very much. I will drop you an email with once Prem has completed his answers and with information on how to access this talk. As ever, if you have questions about anything to do with this or studying at Swansea, do please drop me a line. Okay, thank you.